Sara is somebody with a wealth of expertise that is really hard to capture in just a couple of minutes. And so the thing that is really easy to explain is where she went to school, because it all goes to Cambridge. And as a matter of fact, most of it goes to Harvard. So she's an undergraduate and a graduate student. All of her degrees, all degrees you could get from Harvard, she has, including her PhD. But she also has an MPhil from Cambridge, because apparently writing Cambridge in her address is very important. So anyway, so she's very well trained as a historian of science, and her expertise goes across many different fields. And some of you who've been to the collection of historical scientific instruments, where she has served as the curator since 2000, have seen this big assortment of exhibits. And before that, she was at the Adler Planetarium in Chicago. I don't know if anybody is from Chicago, but her main interests, I think, are in astronomy and the history of astronomy. And I've had the honor of working with Sara over the last few years, because we're making this big course on prediction and people's interests in knowing the future. And Sara's going to talk to you about a different course. These are both courses that are available online through HarvardX and edX. And the other course that Sara's been very involved with led even to a book called Tangible Things, and she's going to talk to you about that tonight. But I'll just tell you that in the context of the other course, the prediction course where I've worked with Sara, she's told me things that I didn't know and that hardly anybody else knows about comets, about navigation, about clocks, about timekeeping, about computers, how to restore telescopes, how telescopes work, who did what, all kinds of gossipy stories about the history of astronomy. And I don't know how much of that Sara's going to share with us tonight, but I do know that I should be quiet and let you hear from Sara. And I'm just very grateful to call Sara my collaborator and my friend. Thank you very much.
Thank you, Jane and Alyssa, for those lovely opening remarks. So, tangible things of American astronomy. As a science that studies distant celestial objects, astronomy deals with few things that can be touched directly. And yet, astronomy has many tangible things, scientific instruments and observatories, for example, which link the past to the present. Now, there's little question about maintaining things still valuable for scientific research purposes. But why should we care about documenting and preserving the old and obsolete? Well, as a historian, I am not going to tell you that everything old is valuable. Far from it. But I will say that there's a lot to be learned from many old things. And this is not just a case of nostalgia. Indeed, outmoded objects, when critically examined, are useful to modern scientists because they offer insight into why things are the way they are, why we believe what we believe, and perhaps how we can change them. So let's take a look at some examples. So, The Adventures of Captain John Smith, Pocahontas, and a Sundial. As our story opens in 1607, we find Captain Smith paddling upstream through the Virginia wilderness when he is ambushed by Indians, held prisoner, and repeatedly threatened with death. His life is spared first by the intervention of his sundial, whose spinning compass needle fascinates his captors, and then by Pocahontas, the chief's daughter, who throws herself between Smith and a warrior ready to bash in his head. And here you see this scene where she's actually quite a young girl at the bottom here, trying to protect him. So Smith called his globe sundial a globe-like jewel that showed the roundness of the earth, the course of the sun, moon, and stars. The outer surface was a sphere marked with the ecliptic, the equator, and the tropics of Cancer and Capricorn. Inside, a compass needle imitated the magnetic virtues of the earth. A gnomon was mounted over the magnetic compass, and its shadow was used to find the time. The other hemisphere held a lunar volvel, which is essentially an analog computer to determine the phases of the moon and the information needed to use the sundial by moonlight. Now, Smith saw his sundial as a microcosm of the universe. While stalling for time among the Indians, Smith claimed that he lectured them about astronomy, geography, and the diversity of nations using this sundial as a prop. Now, Smith believed that mathematics was the key to unlock nature's secrets. His sundial was but one of many mathematical instruments and methods the ship captain used to explore and chart the waters of Virginia and New England. Smith's account of his escape by virtue of his compass dial makes it clear that he understood how mathematical practice gave European settlers powers that seemed magical to Native Americans, powers that would enable them to dominate the New World. Thomas Harriot, the astronomer explorer who had spent 9 months at Roanoke Island in 1585, observed the same thing. He wrote, "Mathematical instruments, sea compasses, the virtue of the lodestone in drawing iron, a perspective glass whereby was showed many strange sights, burning glasses, wild fireworks, guns, books, writing and reading, spring clocks that seemed to go of themselves, and many other things that we had were so strange unto them that they thought they were rather the works of gods than of men." From these first encounters, English cosmology was set on a collision course with the world of the Native Americans. An almanac, a sermon, and mechanical models. Now, as the only periodicals in 17th century New England, what do almanacs tell us? Starting in 1639, they were prepared by Harvard College tutors and printed on a little press in Harvard Yard. They show familiarity with the work of Copernicus, Galileo, and Kepler. But as you can see from the title page of this almanac from 1684, they expressed a Puritan and Christian worldview. So for starters, you can see here how it says it's not just the almanac for the year 1684, but it goes on to say this being, from the year from the creation of the world, 5,633 years, from the suffering of our Savior, 1651 years, and so on, up through the restoration of King Charles II and the last leap year. But down lower, at the bottom here, you'll see this Latin phrase, which I've written up above, and it translates as follows: "The stars govern men, but God governs the stars." Now, Puritans encouraged the study of nature, but believed that natural events reflected God's will and should be seen as signs of the times. After learning that Harvard's commencement was scheduled for the date of a solar eclipse in 1684, the college moved it up a day just to be safe. Only on July 1st, the academic festivities went on without a hitch. But President John Rogers unfortunately died the next day during the eclipse. The owner of this almanac, Judge Samuel Sewall, a hanging judge during the Salem witch trials of 1692, has noted the coincidence in his copy. You'll see his mark on the lower right. It's even more poignant since this issue of the almanac had been a gift to him from President Rogers himself. Now, Rogers' successor as president of Harvard College was Increase Mather, the Puritan divine. In the early 1680s, Mather had viewed the Great Comet of 1680 and 81 and Halley's Comet of 1682 with the college's first telescope. The observations of one spectator, a certain Thomas Brattle, better known probably to you for the street named after his family, His observations were immortalized in Newton's Principia, but Mather's were more put into sermons. Mather preached that comets were warning guns that God discharged before his murdering pieces went off. They were portents of political and religious evils, death, and destruction. And here you see an example of one of his sermons about the comets. And I'll just point out that this was, the printing for this was paid for by Judge Samuel Sewall, who we just met a moment ago. Now, by the time Halley's comet made its first predicted return in 1759, comets and eclipses were still occasions for public awe, but not alarm. John Winthrop, Harvard's professor of mathematics and natural philosophy, observed the comet in April and gave a public lecture. Following Newton, he said the comets were part of the solar system and brought vital fluids to the Earth and fuel to the sun. God contrived their orbits to prevent collisions. He demonstrated this wisdom with equipment such as this planetarium and cometarium, showing that comets were signs of God's providence and not his punishment. The thing I want you to note well here is these objects, when properly interpreted, show that astronomy had not shed its ties to religion, even though God's role in the cosmos had been reevaluated. In fact, faith was still a motivator for astronomers. Astronomical instruments go behind enemy lines. So, like comets, solar eclipses had also become occasions for research rather than dread in the 18th century. In 1780, Samuel Williams, Winthrop's successor, decided that he would observe a total solar eclipse in Penobscot Bay, Maine, even if the location was in a war zone. The bay was a strategic base for the British Navy during the American Revolution, and just a year earlier had been the site of a major naval battle in which an American fleet was decimated. But Williams was no stranger to research behind enemy lines. As a student in 1761, he had accompanied John Winthrop up to St. John's, Newfoundland, to observe the transit of Venus during the French and Indian War. So let me take a moment just to explain what a transit of Venus is and why you would go all the way to Newfoundland to try to observe it. So a transit of Venus is a rare astronomical alignment of the Earth, Venus, and the Sun. So if you think of the Sun as here and Venus is going around it, and then the Earth is going around both of them, occasionally Venus will cross between the Earth and the Sun. But most often, it's above or below the plane that the Earth and Sun are, so it doesn't cross right in front of the disk of the Sun. But every 105.5 years or 121.5 years, Venus crosses in front of the Sun and looks like a little dot going across. And astronomers, these transits, as they're called, come in pairs 8 years apart with this big gap between. And so in the 18th century, Edmund Halley had suggested that if astronomers went all over the globe and tried to observe this transit, a little dot going across the Sun, from different parts of the globe, they could, in effect, triangulate on Venus and the Sun and therefore figure out the distance from the Earth to the Sun, which was an unmeasured distance at that time. So it was one of the great unsolved problems. So there was a multinational collaboration where astronomers went all over the globe. And the only observer in North America to participate in this was Professor John Winthrop, who took Samuel Williams up to 1761. But he had to go behind enemy lines. And these are some of the instruments that Winthrop had carried, along with letters of safe passage written to British and French commanders. And the expedition had been financed by the colony of Massachusetts Bay. Now, at the time of the second transit, the pair was in 1769, and astronomy also rose above politics then. With assistance from Benjamin Franklin, Harvard imported state-of-the-art English astronomical instruments despite the boycott of English goods by patriotic rebels or the British military blockade of Boston. In 1780 now, the eclipse fell in the midst of the official war. Like Winthrop did before him, Williams turned to a senior statesman and with his help received support from the American Academy of Arts and Sciences and the new Commonwealth of Massachusetts. The state provided use of its row galley, a 250-ton ship powered by oars as well as sail, with 4 swivel guns. The Board of War financed the expedition. John Hancock, who was Speaker of the House in Massachusetts, wrote the following to the British commander at Penobscot. "Though we are politically enemies, it is presumable we shall not dissent from the practice of all civilized people in promoting science." And the officer agreed not to impede the astronomers. So Williams, 2 Harvard faculty members, and 6 students, plus probably a lot of rowers provided by the Commonwealth, the hidden people who aren't always involved in these things, they departed Boston for Penobscot Bay, Maine in October. Now, for security reasons, the British commander limited their stay and forced them to observe from Long Island, now called Islesboro, Maine, rather than from the mainland as planned. Williams had no time to determine the longitude of the new site to see if it would still be within the path of totality. Now, modern calculations place his encampment slightly outside, but he was the first to observe what later became known as Bailey's beads, as we see in this publication. So it shows that he's quite close to the total path. Now, this excursion is credited as being the first solar eclipse expedition in North America. And these are the British instruments that Ben Franklin had ushered through boycotts and blockades to take further by patriots behind British enemy lines to see the eclipse. And there is a lesson here about science rising above politics, and another about having to use the apparatus manufactured by your current enemy. But that's a story of political economy for another day. So I'd like to turn now to astronomy as public utility. A major reason that the state had supported astronomical research was the presumption that astronomy was useful, especially for navigation, geodetic surveys, and timekeeping, all needs of the Commonwealth and federal government. Proof of this premise can be seen in the establishment and early work of the Harvard College Observatory. So let's start by following the money. When the apparition of the Great Comet of 1843 shamed Bostonians into building an observatory worthy of observing it, community leaders ponied up $25,000 in 6 weeks. The preponderance of insurance companies on the dedication plaque underscores the importance of Boston as a mercantile center dependent on shipping. Before the comet, Harvard had convinced William Cranch Bond, who you see here, to bring his own instruments to Cambridge and work for free from a rooftop on the Dana House, which was located at the current site of Lamont Library. Now Bond had all this money, Harvard had all this money, but he could use it to build and direct a monumental observatory with fixed instruments. Harvard bought a refractor from Merz and Mahler of Munich with a 15-inch aperture. So that's the diameter of the lens. It was the twin of the largest in the world at the new Imperial Russian Observatory at Pulkovo. So you see when Harvard gets going, it does nothing by halves here. Now, this telescope, and you see it pictured there, It's still up at the observatory. It remained the largest in the United States for 25 years when it was surpassed by the U.S. Naval Observatory's 26-inch telescope. And here is a big change. In 1847, the best telescope had to come from Germany. 25 years later, it was made down the street in Cambridgeport, Massachusetts. Bond and his sons, George, Joseph, and Richard, were astronomers and horologists living at the observatory. Not only did they work at the observatory as well as live there, but they were also partners in the family clockmaking firm, William Bond and Son. The entanglement is revealed by this letterhead. So here is a bill for regulating, I believe, a chronometer, and here's the company name. And up here, they're not showing their offices in Boston. They're showing the observatory and Garden Street. In 1849 and 1850, Bond devised what became known as the American method of astronomical observation. The new method employed new astronomical instruments invented by the Bonds. First, there was a clock with an electrical brake circuit that could send time signals along wires to a drum chronograph, which you see here in the front, that recorded the beats of the clock on that paper. And then you have an astronomer who is observing the sky through a transit telescope. And he can press a telegraph key when a star crosses in front of his micrometer eyepiece. And that moment of observation is marked along the time chart on the paper on the chronograph. Now, this new American method took European observatories by storm. It was far more accurate than the old ear, eye, hand method, in which the astronomer would listen to and count the beats of the clock while simultaneously watching the transit of a star and then jotting down the instant when it crossed a wire in his field of view and estimating the fractions of a second in which that happened. Now, when the new clock and chronograph were displayed at the Great Exhibition in London in 1851, they earned a bronze medal for the company and were lauded in the publication American Superiority at the World's Fair. Now, the telegraph lines that carried time signals inside the observatory could reach beyond its walls. And before long, Harvard was selling time. With the assistance of the U.S. Coast Survey, wires linked the Harvard College Observatory in Cambridge to the shop of William Bond and Son in Boston. When the New England Association of Railroad Superintendents, which represented 15 different companies, voted in 1849 to adopt a standard time along all the tracks in the interest of public safety and convenient scheduling, it decided that the time to be regulated by William Bond and Son. And you see this timetable here of which conductors need to bring their watches for regulation on which days. The firm used chronometers to adjust railroad conductors' timepieces and installed astronomical regulators in railroad stations. The first of these standard clocks was Bond number 137, which was delivered in 1855 to the Boston and Providence Railroad for use in the Boston station. Bond clock number 394, also shown here, was one of the regulators set up at Harvard Observatory to deliver standard mean time to New England through the agency of the Bond firm. So the Bond firm profited from the business, but Harvard College Observatory delivered the signal for free under the directorships of William Cranch Bond and then his son George Phillips Bond. Not until 1872, under the leadership of Joseph Winlock, did the observatory establish fees for its time service. Now, Bond was also a pioneer in celestial photography, taking the first photograph of a star other than the sun in 1850, using that great refractor we saw a moment ago, as well as daguerreotypes of the moon and a solar eclipse. And I'd like to turn now to some more photography and talk about glass that altered the scale of the universe and the workforce. So I want to take you and jump ahead some 50 years to the directorship of Edward C. Pickering and photographs made on glass plates by huge camera-like telescopes. Pickering was a pioneer of the new field of astrophysics. He wasn't interested in simply stars' positions, but their physical nature as revealed by photometry and spectroscopy. Initially, he and male observers made these measurements at the eyepiece of telescopes and photometers, but photographs, more sensitive than the naked eye, soon took over the data capture. Pickering deployed photographic telescopes in both hemispheres. Notable among them was the Bruce telescope. Carrying a price tag of $50,000, which was $66.5 million in today's money, it was the most powerful telescope in the world when completed in 1893. It was made by Alvin Clark and Sons of Cambridge, Massachusetts, and the telescope had 2 pairs of massive glass lenses with a clear aperture of 24 inches and a combined focal length of 11 feet. And here what you're seeing is the 2 pairs of lenses mounted freely on a stand in our gallery. And what's in front here is another giant piece of glass, a removable prism for dispersing starlight into spectra. And on the right here, you see the lenses would have been here, and the objective prism up here. And the plate holder where the photographs were taken are down here. Now, the telescope was sent by Harvard College to an observatory in Arequipa, Peru, that it built, and then on to Bloemfontein, South Africa, in order to photograph the southern sky on these giant glass plates. A single photographic plate could reveal more than 100,000 stars. When the objective prism was put in front of the plate, the photographs showed starlight dispersed into bands of spectra, like you see here. They look like little smears with lines on them. Now, each of these spectra offers information on the elements composing the star, whether the star had an orbiting companion, how it was moving, what its temperature was. And the information was used at the observatory to classify stars according to a type sequence that was OBAFGKM, which was devised by Annie Jump Cannon and the other women working with her at the observatory, and well remembered by the later mnemonic, "Oh, be a fine girl, kiss me." But that didn't come from the ladies at the observatory. Another concern was the changing brightness of stars over time. To measure this, photographs were examined under magnification, and the variable star's image was compared to magnitude standards on a fly spanker, like you see here, that was slapped down alongside on the plate. Notes were made in India ink on the non-emulsion side of the photographic plate, on its paper sleeve, and in pencil in a logbook. Now, these annotations leave a trail of how the work was done, by whom, and when. I wish I could say it was an indelible trail, but recent projects to digitize the plates have been scrubbing off these marks. This irreversible act is of great concern to historians as well as many plate-using astronomers. Henrietta Swan Leavitt was a computer at the Harvard College Observatory who specialized in variable stars and examined many Bruce plates. Her analysis of a special class of variables, known as Cepheid variables, in the Magellanic Clouds led to her discovery of a law connecting the absolute magnitude of each such star with the period that its brightness fluctuated. Now, she published her findings in 1908 and 1912, and they would soon be used as a way to measure the dimensions of the universe. So when Edwin Hubble in the 1920s, using a 100-inch telescope at Mount Wilson Observatory, discovered this type of Cepheid variable star in spiral nebulae within the Milky Way, it became clear that these nebulae, these fuzzy patches, were independent galaxies located far beyond our galaxy. So prior to this time, there was a common view that the Milky Way was everything, and everything was contained in it. And so now we see that these things that look like starry patches were actually full galaxies at a great distance. And Leavitt's findings were able to act like a standard candle for measuring those distances, because you could tell what the brightness should be by how much they flickered, in effect, like how they fluctuated in light. And so then if the brightness wasn't that much, as observed on the plates, then it had to mean that it was just that object was much further away. And so that's how we got these great distances. And in 2008, the American Astronomical Society recognized the significance of Leavitt's work by designating the period luminosity relationship as the Leavitt law. So with instruments readied in Cambridge before being shipped abroad and crates of glass plates returned for analysis, the observatory had become a research factory. To manage all the observing stations and the data streams, Pickering employed the most fantastic desk in the history of astronomy. Custom made by the observatory's chief engineer, the desk is 8 feet in diameter with 12 drawers, rotating around a central pole. A bookcase rotates independently above it. Here we see the remnants of a label on a compartment marked Boyden Station, which was the name of the observing station first in Peru and then in South Africa. Pickering's successor, Harlow Shapley, also loved the rotating desk and was often photographed at it. So, paper dolls and Wonder Women. The reduction of the data from hundreds of thousands of astronomical photographs was time-consuming, and Pickering could not afford to hire more men. He turned to the daughters of Harvard faculty, qualified Radcliffe students in unpaid internships, and women willing to work for 25 cents an hour. Between 1885 and 1927, 80 women computers, as they were known, analyzed the data contained on all those glass plates produced by Harvard's photographic telescopes. Shapley measured projects in terms of what he called kilogirl hours. Now, notwithstanding that Miss Catherine Bruce and Mrs. Mary Anna Palmer Draper funded a lot of this work, the women were actually not treated very well by the university. Take, for instance, Annie Jump Cannon. Now, she personally classified more than 350,000 stars by their spectra and created the Harvard classification system still used today. She was elected the first female officer of the American Astronomical Society in 1912, and her astrophysical work earned her many accolades during her lifetime. And yet, Harvard refused to grant her a faculty appointment until 1938. In spite of all the pioneering work of computers such as Cannon and Leavitt, this 1980 photograph depicts them holding hands in a paper doll-like pose. It's a charming photo until you start to think about it. Now, I do get some satisfaction in seeing Cannon's life story featured in 1949 in Wonder Women of History, a series bound with the Wonder Woman comic books. But this comic strip is in sharp contrast to the depiction of female astronomers in the media. dressed in high heels, short skirts, and white evening gloves. Women are posed next to fancy telescopes marketed to men. Puns are made about heavenly bodies. These are the stereotypes that prominent women astronomers, such as Vera Rubin and Virginia Trimble, had to overcome in the 60s, 70s, and 80s. So what does a computer have in common with a teapot? Well, this brings up the topic of popular culture and the public's fascination with things astronomical and how that it has been mobilized to advertise products and support research. Astronomers, of course, were not secluded on Observatory Hill, nor were they removed from the social rituals, entertainments, business, and politics of their times. William Cranch Bond, for instance, took the time to have this life mask made in 1844, and we could look at it like his photographs and chronographs as capturing an instant in time. This silver tea set, engraved with the initials AJC, brings to mind the work of its owner, Annie Jump Cannon, a computer who daily assigned alphabet letters to the stars she classified. Cannon enjoyed serving tea in her home, Star Cottage, on Bond Street alongside Observatory Hill. She used one of her logbooks to record her various guests and visitors. Or consider that in 1879, only a year after Gilbert and Sullivan produced HMS Pinafore, a Harvard astronomer wrote a parody based on observatory life. Now, like, how many songs do you know about prisms and photometers? This is where you'll find them. 50 years later, it was performed by another generation at the observatory. On the flip side, ephemeral publications such as greeting cards, advertisements, and vinyl records illustrate how contemporary popular culture drew inspiration from astronomers' work and the celestial bodies they studied. Sheet music and recordings brought the stars home. So did products promising their users an out-of-this-world experience. Deserta drew on the anticipated return of Comet Halley in 1910 to launch its new pudding. Excitement over the opening of the world's largest telescope in 1949, the 200-inch telescope at Palomar Observatory, California, was used to sell Buicks and bread. The associations promoted how high-tech and innovative the goods were. In some cases, profits went to support astronomy. Take, for instance, this Warner's Safe Yeast trade card featuring children looking at a comet. The product was part of the patent medicine empire that made Hobart H. Warner a millionaire. He used his fortune to build the Warner Observatory in Rochester, create various comet prizes, and finance Lewis Swift and E. E. Barnard, two eminent astronomers. So what about homemade and recycled telescopes? Any object-based history of American astronomy should take into account amateur telescope makers, whose mecca is Stellafane, shown here, and participants in groups such as the American Association of Variable Star Observers. But I'd like to take a moment to focus on Operation Moonwatch. During the International Geophysical Year, which ran from July 1957 through December 1958, and yes, that's more than a year, and it was the largest multinational collaboration of scientists up at that time. But during that year, the United States and the Soviet Union planned to launch the first artificial satellites to study the Earth's shape and atmosphere. The satellites would need to be tracked, and the job was given to Fred Whipple, an expert on meteor tracking and photography. As director of the Smithsonian Astrophysical Observatory, Whipple planned a two-pronged professional and amateur approach. 12 professionally manned Baker-Nunn telescopes were to be deployed to photograph the satellites in order to determine their orbits. But the big cameras needed to know where to look for these faint objects. This was the job of Operation Moonwatch. The Smithsonian Observatory published inserts in Sky and Telescope magazine that called for the formation of teams of amateurs who would observe the satellites passing overhead and relay their data back to the observatory. They were equipped with modified Army M17 elbow telescopes and cheap satellite tracking telescopes made specifically for this purpose. But when Sputnik launched unexpectedly on October 4th, 1957, the United States was caught with its professional telescopes down. The Moonwatch observations of citizen scientists filled the breach. Project Moonwatch speaks to the importance of amateurs and crowdsourcing in giving an assist to professional astronomers. It also speaks to the entwinement of military, security, and astronomical institutions in the development and deployment of high-tech, often classified optical instruments. So, to draw some conclusions here, I'd like to return to what I said at the start of this talk when I asked, why should we care about documenting and preserving the old and obsolete? Now, a simple answer is that material things enhance our knowledge of astronomy's history in ways that written texts alone cannot do. But I think a more important answer is that learning about the past helps us to live critically in the present. Captain Smith's Sundial sheds light on the imperialistic arrogance of colonizers and the roots of conflict with native peoples about cosmology, an ongoing situation in the location of mountaintop observatories. Mechanical models of the solar system must be understood along with almanacs and sermons, not only as a means to teach astronomy, but also to promote piety in colonial New England. They lead us to ask how changing religious beliefs in America today might affect academic and federal support for science. Clocks, telescopes, and quadrants taken behind enemy lines on research expeditions declare not only a noble commitment to place science above politics, but also the importance of state funding to support the work. These are both worthy but difficult goals still. And then we saw how the improved clocks, chronographs, and telegraph wires were deployed to increase astronomical accuracy and deliver standard time as a public utility. Motivation came from a partnership between business and astronomy, represented in the entanglement of personnel of the Harvard College Observatory and the William Bond & Son firm. The story of glass in the form of large lenses, prisms, and photographic plates takes us into a global network of observing stations, an expanded astronomy workforce, and the creation of a data library which can still be mined for information 100 years later. The observatory director has become a business manager, seated at an enormous desk when he is not out raising money. The glass plates and paper ephemera also raise our consciousness about the role and treatment of women over time. And Moonwatch telescopes show us the power and value of amateurs. Astronomers, of course, have always imbibed the values of their times, as tea sets, images of baseball, and life masks remind us. The thing, though, is to us to be mindful of the public's romance with the stars, and remember how popular media can be used to build support for dark skies and great new telescopes. So to close my talk, I just want to say that many of the objects that I showed you tonight are on display in 2 galleries in the Science Center at the Collection of Historical Scientific Instruments. Many are on display in the Putnam Gallery on the first floor of the Science Center, and an exhibit called Time, Life, and Matter, Science in Cambridge. And on the 3rd floor, at the foyer of the History of Science Department, we have a little gallery where we have an exhibit called Starstruck, Astronomers in Popular Culture. And the exhibit there was curated by 9 students from the Tangible Things course that Laurel Thatcher Ulrich and I co-taught last fall. And you'll see in it the T-set, the life mask, Moonwatch telescopes, many of the things that you also saw in this talk. And I may have some of the students who co-curated that exhibit with me here in the audience. I see one in the back, Isabella, I think. And so if you're interested in that project, do speak to her. The other thing, these exhibits are open both are open on weekdays, and the one in the Putnam Gallery is also open on Sundays. So you'll have an opportunity to see both exhibits. One's permanent, one's temporary, but it'll be up till the end of September. The one called Starstruck, Astronomers of Popular Culture. So I do encourage you to come see the real thing. Thank you.